The carrier deck trembled before sunrise. Engines coughed in the dark, propellers cutting mist into sheets of silver vapor. Sailors moved under the dim glow of red lamps, their faces streaked with oil and salt. Along the starboard edge of the flight deck, a group of F-4U Corsairs stood armed with something no one had ever seen before: a single rocket, nearly 10 feet long, slung under each fuselage like a steel torpedo with fins. The pilots called it the Tiny Tim, but there was nothing tiny about it. Each one weighed over 1,000 pounds, more than half the load of a dive bomber, and its warhead held the same explosive charge as a 500-pound bomb. It looked too large for a single-engine fighter to even lift. As the first Corsair roared forward, the deck crews braced. The aircraft staggered for a heartbeat, wheels barely clearing the edge before climbing into dawn. Below, destroyers and escort carriers turned into position, while far ahead, in the morning haze of Cure Harbor, Japanese anti-aircraft gunners manned their posts. They had spent months reinforcing their submarine pens. Reinforced concrete, 3 meters thick, proofed against the heaviest bombs the Americans had. From inside, the crews could hear distant thunder from the approaching planes and thought nothing of it. Then the sky flashed. A streak of light tore downward like a falling star. A single Tiny Tim struck the pen's roof, and the entire structure lifted off its foundations. Concrete fractured, steel doors bent inward, water erupted into fire. Inside, men who'd survived every previous raid saw daylight through what had once been solid earth. It wasn't a bomb. It wasn't a torpedo. It was the moment every fortress designer in Japan realized that no wall could save them anymore. The age of armor had ended, and in its place, the age of velocity had begun. Fortresses that couldn't be touched. By the start of 1945, Japan had turned its coastline into a continent of bunkers. Every harbor, every inlet, every island that could hide a destroyer or submarine was shielded by reinforced concrete pens, thick as bunkers, roofed with rebar and gravel, disguised under camouflage netting. After 3 years of watching American carrier aircraft level cities and shipyards, the Imperial Navy had one obsession left: survival beneath the surface. At Kure, Sasebo, Yokosuka, and dozens of smaller naval bases, entire fleets vanished underground. Submarines hid inside cavern tunnels carved into the rock. Destroyers rested in vaulted shelters built into mountainsides. Even at Okinawa, coastal escarpments were blasted open to form bomb-proof bays. American intelligence photographs showed little more than shadows. Long slits carved into gray rock, framed by seawalls. For the Allies, this was a new kind of problem. By 1944, U.S. carrier aviation had achieved absolute dominance of the Pacific skies. Task Force 58, and the Fast Carrier Task Force could send hundreds of aircraft against any target in a single morning. But bombs, even the massive 2,000-pound armor-piercing types, were struggling to make an impression on Japan's hardened pens. Crews flying Helldivers and Avengers could land perfect hits on these fortresses, only to watch the explosions wash harmlessly across concrete. The Japanese, who had suffered catastrophic losses at Truk, Rabaul, and the Marshalls, had learned the lesson of exposure. They would not fight in open harbors again. Every surviving submarine, escort, and minesweeper now slept beneath meters of stone. They had built a world designed to outlast the bomb. The limits of firepower. The problem was simple physics. Bombs depended on gravity and angle. They fell vertically, their force dissipating over wide impact zones. Even a 1,000-pound bomb striking directly on concrete rarely achieved penetration deeper than 1 meter. To destroy a hardened pen, a bomber would need to hit the same point repeatedly, from high altitude through smoke and flak. In practice, that never happened. Torpedoes were no better. The pen's entrances were too small, too shallow, and heavily netted. The few Japanese destroyers and escorts that still ventured outside were often shielded by breakwaters that turned torpedoes away or detonated them prematurely. The Americans could control the air, but they couldn't always reach the enemy's heart. What the Navy needed wasn't a bomb. It was a directed projectile, one that could strike horizontally at high velocity and deliver all its energy into the same square yard of armor. A weapon compact enough for a single aircraft but strong enough to equal a naval shell. A weapon that could punch, not just explode. The spark of an idea. The inspiration came not from the carrier decks but from testing ranges back home, specifically the Naval Proving Ground at Dahlgren, Virginia, and the Naval Ordnance Test Station at China Lake, California. There, engineers were experimenting with scaling up aircraft rockets. The existing 5-inch HVAR, the high-velocity aircraft rocket, had already proven devastating against shipping and armor. But against concrete, it lacked weight. It was accurate, fast, and cheap, but its warhead was too small to break through a bunker. In mid-1944, a small team led by Lieutenant CMDR Calvin Bolster proposed something audacious, a rocket 10 times larger, using a modified 500-pound bomb casing as its warhead, and powered by a giant solid-fuel motor derived from naval depth charges. It would weigh 1,280 pounds, accelerate to over 800 feet per second, and hit like an artillery shell fired from the sky. They called it, half in jest, the Tiny Tim. Its name came from Charles Dickens' frail child character, chosen by engineers with a dark sense of humor. But there was nothing frail about it. The weapon was more than twice the size of any rocket yet carried by a fighter. It required a special launch tube, welded directly to the aircraft's belly. When fired, it left the plane with a roar and a backblast so violent that early test pilots described it as being kicked by God. A weapon in search of a war by autumn 1944, the Navy's Bureau of Ordnance approved field tests. Tiny Tim rockets were sent to China Lake and Patuxent River for evaluation on F-6F Hellcats, F-4U Corsairs, and TBF Avengers. Pilots trained to drop from low altitude, 1,500 to 3,000 feet, aiming for horizontal impact at shallow angles. The rocket's proximity fuse and armor-piercing nose allowed it to penetrate deep into reinforced targets before detonating. Observers watched in disbelief as the first live test obliterated a full-scale concrete bunker. The shockwave snapped range markers in half. When the dust cleared, the reinforced roof, 4 feet thick, was gone. A single rocket had done what dozens of bombs could not. The ordnance officer's report summarized it dryly. Performance exceeds expectations. Capable of defeating all known fortifications within operational range. In Washington, planners took note. They had finally found a weapon that could make every concrete fortress in Japan obsolete. And soon, that weapon would meet the very bunkers it was built to destroy, from range table to rocket, building the Tiny Tim and teaching men to fire it. Once the problem was understood, that hardened pens, vaults, and buried slips would shrug off bombs, the Navy set about building a new kind of striker. The Tiny Tim was the answer, a rocket that put the punch of a 500-pound bomb into a single, direct, high-energy impact from aircraft. It was not a clever guided missile. It was simpler and, in combat, brutally effective. Mass, velocity, and a hardened, no-second fuse to detonate after penetration design. Work concentrated at the Navy's Ordnance Centers, the Naval Proving Ground, and the Naval Ordnance Test Station at China Lake, where ordnance engineers and test pilots pushed aircraft rockets far beyond the established envelope. The Tiny Tim was big in every sense, roughly 11 3/4 inches in diameter and almost 10 feet long. Its warhead used a bomb-sized charge, its motor a massive single-grain solid propellant. Mounted on a special pylon and launch rail, the rocket sat under the fuselage like an ungainly lance. Early trials proved the concept. Hit the roof or side of a reinforced shelter and the rocket's hardened nose would bite through. The fuse would delay a heartbeat, and the warhead would detonate inside. The structure's resistance turned into its own undoing. That success, however, belied a long list of technical and operational challenges. Tiny Tim's mass and thrust created extraordinary stresses. Single-engine fighters that carried it needed reinforced hardpoints and modified balance calculations. When fired, the rocket produced a violent backblast and a torque that could yaw a light airframe. Pilots required new procedures to keep the aircraft steady through launch and the initial seconds of its flight. Ground crews had to weld special rails, design safe handling procedures for the heavy ordnance, and train deck crews to move rockets that would not fit the usual bomb dollies. Equally critical was the fuse. Ordnance officers tested both instantaneous and delayed action impact fuses, so the rocket would penetrate concrete and detonate within, rather than disintegrate on contact. Ballistic trials measured nose shapes, standoff, and angle of attack. Penetration was a product of speed, and the nose's design just as much as explosive power. Final test shots at ranges and on concrete mock-ups showed that a single Tiny Tim, delivered at a shallow trajectory from low altitude, could fracture slabs and collapse vaults that had resisted repeated dive bombing. Training turned the engineering into practice. Pilots accustomed to toss bombing and glide runs had to learn new profiles: low-level approaches, precise sighting, and an acceptance that the aircraft would be subjected to violent forces at launch. For carrier operations, that meant special deck procedures. Launching a 10-foot rocket from a carrier required exactly timed deck runs, ballast adjustments, and sometimes the support of two engine types like the torpedo bomber or the sturdier single-engine fighters that could shoulder the load. Crews practiced in calm weather under the careful eye of test pilots. Instructors emphasized one immutable rule: get the aim right, because Tiny Tim did not offer a second chance. Operational doctrine followed quickly. Rather than saturate a target with bombs, strike planners could now assign single-pass, high-value shots: a pen entrance, a dry dock gate, the bridge of an escort. Aircraft would approach low and fast, aim for a structural weak point identified by photo reconnaissance, and deliver one rocket to a precise square yard. Reconnaissance photo interpreters learned to spot seams, bolt patterns, and sloped surfaces that would make the biggest difference. Intelligence briefings told pilots where the rebar lay and how thick the roofs were. Ordnance officers gave them the fuse setting that would most likely detonate after penetration. On the other side of the world, Japanese coastal commanders continued to reinforce and disperse, unaware that the Allies were carrying not just larger bombs but a new method: a projectile designed to concentrate energy into a single, projectile-driven strike. The pens that had seemed invulnerable in aerial photographs suddenly had thin places exposed by human analysis, and by the blunt arithmetic of mass and momentum. The Tiny Tim moved, from test range to front line in a matter of months. Early combat flights showed the learning curve. Pilots adapted to the launch shock, ordnance teams refined handling, and decks got used to the new choreography. When the rocket finally met its target, a fortified pen or a close-in escort, the effect was often instant and catastrophic. The weapon's arrival on the scene would force a rethinking of harbor defense and naval construction, and it would force crews, ordnance men, and strategists alike to confront a simple, unwelcome truth: concrete could be broken in a single pass. The men who built and fired the monster. At first glance, the Tiny Tim looked impossible. On the carrier decks and at the naval air stations, it seemed absurd that a single-engine fighter could lift something so large. Yet behind that ungainly rocket was a line of men who refused to accept that any wall could be truly bomb-proof. The makers in the desert of California, at the newly founded Naval Ordnance Test Station. Engineers lived among chalk dust and heat haze. They welded prototypes in tin sheds, sketched fin shapes on packing paper, and slept beside the range. They came from Caltech, Douglas, the Bureau of Ordnance, physicists, machinists, draftsmen, and mathematicians bound by one conviction: that speed could do what weight could not. Every test meant risk. Misfires blew sand through the workshops. Fuel grains cracked and exploded. Rockets tore themselves apart on launch rails. Yet each failure taught them something measurable: the right propellant temperature, the perfect cone angle, the exact millisecond of fuse delay. By winter 1944, they had turned sketches into a weapon that could travel a mile in 5 seconds and break reinforced concrete as though it were glass. The flyers, then came the pilots, the men who would have to trust it. At Patuxent River and China Lake, they lined up for briefings that read more like warnings. "You'll feel a kick," one instructor said. "Don't fight it. Just fly through it." The first few launches were chaos. Corsairs veering off course, Hellcats jolting into stalls, Avengers losing altitude the moment the rocket left the rail. Flight surgeons grounded men with bruised shoulders and cracked ribs from the recoil shock. Still, they volunteered, adjusting trim tabs, adding ballast, learning to time the trigger so the rocket left clean. What united them was curiosity as much as courage. They wanted to see if it could be done, if a pilot could aim a weapon that big with nothing but sight and instinct. When it worked, the feeling bordered on disbelief. Pilots wrote in their logbooks simple notes. "Fired 1 Tiny Tim. Hit target. Total destruction." The deck crews. On the carriers, the deck gangs adapted fastest. They called the rockets flying stovepipes. Loading one required half a dozen men, slings, and a prayer. The ordnance teams worked in sweat and fumes, bolting launch rails under the bellies of aircraft, wiring the ignition leads by hand. They moved with ritual precision. Check the fuse pin, secure the safety wire, signal the pilot. Any mistake could turn the deck into an inferno. They understood better than anyone that each rocket carried not just TNT but hours of human labor and calculation. When a pilot returned with the rail empty, the crew watched him taxi in silence, reading his face for the answer before he spoke. Together, engineers, pilots, sailors, they formed a single chain of trust. Each launch was a handshake between invention and courage, between the men who built the weapon and the men who had to believe in it. Tactics, tech, and the moment rockets became strategy. Tiny Tim was not simply a bigger bomb on a stick. It was a change in logic, a way to concentrate force in a square yard instead of a scatter of craters. Once pilots and planners understood that a single rocket could breach armor and concrete alike, doctrine shifted from saturation to precision, from repeated sorties to single, decisive passes. From HVAR to heavy hitter, the high-velocity aircraft rocket, HVAR, had taught aviators to aim small, fast, and low. HVAR was accurate and lethal against light armor and ship's superstructure, but it lacked the mass to break reinforced shelters. Tiny Tim borrowed HVAR's lessons, low-level runs, steep aiming, and single-pass delivery, then multiplied the effect by weight and momentum. The rocket's mass, coupled with a hardened nose and a delay fuse, permitted penetration. It punched a hole, then detonated inside. That was the moment aircraft stopped being merely spotters or bombers for naval guns and became direct penetration artillery in their own right. Photo interpretation. Became ballistics targets changed from vague zones to specific weak points. Intelligence officers learned to read seams in concrete, bolt lines, rebar shadows on reconnaissance photos. Planners began marking aim points on maps. Not just where to hit, but how to hit. Angle, altitude, airspeed, and fuse setting. A ship's escort might be vulnerable at the bridge or amidships. A sub-pen's weakest seam would be the roof joint or the ventilation throat. A successful strike was the product of combined analysis. A photo interpreter, an ordnance officer, and a pilot who could fly a profile to a handful of feet. Carrier air groups rehearsed like artillery batteries. Carrier air groups adapted like artillery batteries. Instead of mass dive bombing runs, they practiced timed single runs at multiple targets. One Tiny Tim to breach the pen, HVARs and rockets to suppress flank defenses, and follow-on bombers to exploit the hole. Coordination became surgical. The strike commander's role was to sequence effects. The rocket comes first. The blast opens the roof. The bomber follows, incendiaries spread, and boarding parties, or submarine-launched small craft, then struck at exposed ships or installations. The effect was multiplication. One rocket made dozens of subsequent explosives effective where they would otherwise have wasted their energy. A new kind of risk and reward. Tactically, Tiny Tim demanded bravery and discipline. Attacking aircraft flew low enough to be shot at by light flak and small arms fire. Pilots had to accept that one pass might be the only pass. There was no circling back while AA reloaded. That risk was balanced by reward. A single successful hit could endanger a fleet or render a harbor useless for months. Escort destroyers that had once danced along channel mouths found themselves vulnerable to a weapon that arrived like thunder and left structural truth in its wake. From rocket to missile, a conceptual leap tiny. TIM was also a conceptual bridge. It taught militaries the value of kinetic delivery over pure explosive weight, that speed plus concentration could defeat sheer mass. Engineers watching range footage took notes on nose shapes, chamber delay, and penetration dynamics. Tactical thinkers realized that guidance was desirable but not always necessary. Sometimes clever placement, velocity, and timing were enough. The rocket's success accelerated interest in standoff precision. The missile age did not begin with guidance alone. It began with the demonstration that a single, well-placed kinetic strike could achieve strategic effects. The enemy's doctrine rewritten. For Japanese planners, Tiny Tim forced a doctrinal reset. Fortifications designed to absorb blast now instead inwardly collapsed under the stress of a penetrating detonation. Convoy escorts could not rely on the shelter of a breakwater or a gatehouse if one strike could breach them and allow subsequent attacks to flood the harbor. Defense became dispersal and concealment rather than concentration in concrete pens, a costly and often impractical change at a late stage of the war. Tiny Tim rewired the logic of a power projection from the air. Precision, velocity, and an understanding of structure replaced brute explosive mass. Its first battlefield proofs would come quickly and harshly, moments when a single rocket would not only break concrete, but break certainty itself. The day roofs split. Tiny Tim in combat. The first time a Tiny Tim met a concrete pen in anger, the sky was iron and the sea a sheet of pewter. Carrier decks ahead of target launched on a timetable measured in minutes. Pilots checked sights twice. Ordnance crews shut down radios and watched the horizon through smoked glass. What followed was not a carpet of bombs but the single, terrible geometry of a rocket aimed at a single point. This is a composite reconstruction drawn from multiple after-action reports and pilot logs. The small, repeated stories that together show how Tiny Tim altered the rules of attack. Approach, the calm before the swan. Dive a fighter or torpedo bomber climbs out of the carrier's wind with the rocket slung beneath it. The pilot runs a final checklist. Trim tabs set aft, ignition wires checked, pylon pins secured. The plane rolls into formation, joins the strike group, and then, at the marshal bearing over the rendezvous point, peels toward the coast. Below, reconnaissance photos have already done their work. Intelligence marked an aim point. The seam where pen roof met the seawall, a bolt line, a vent shaft, a weakness identified by shadows and scale. Strike controllers brief the pilot. Altitude 1,800 feet. Attack angle 15 degrees, airspeed 240 knots, fuse delay set to penetrate roughly 6 to 8 inches of rebar-reinforced concrete before detonation. The pilot lines up. Light tracers from flak pepper the air ahead like angry stars. He breathes steady. This is the one pass. A miss wastes not only a rocket but the element of surprise. The firing moment, a kick and a silence. At the trigger, the aircraft feels the world shift. The launch is accompanied by a guttural roar and a violent kick in the stick. Even seasoned pilots call it a shove from the deck of a battleship. For a heartbeat, the fuselage quivers and the sight. Picture skates as the rocket clears the rail and begins its ballistic arc. Then silence, a few seconds of taut, cool air while the rocket closes on glass and concrete. From above, it is a streak. From below, it is a falling piece of metal with intent. The Tiny Tim impacts at a shallow angle. The hardened nose bites the concrete, and the delay fuse holds the charge until the warhead has driven through the shell of the structure. Instead of a surface blast that sprays dust and rubble, the explosion happens inside the structure. The roof's interior becomes the fulcrum of destruction. Concrete breaks like paper. The result is more architectural than cinematic. Reinforced slabs that shrugged off hundreds of bombs crumble from within. Rebar that tied slabs together becomes cantilevered, then snapped. Poured concrete shears along stress lines. The roof lifts visibly, shingles of stone and concrete blowing outward in sheets. Doors designed to withstand direct hits. Steel barriers, knuckle-thick hinges, twist inward as support columns fail. Inside the pen, the effect is catastrophic. Water piping crushed, breathing systems ruptured, electrical panels jarred into molten short circuits. A submarine that seemed safe in stillness is suddenly exposed. Hatches blown, ventilation choked with dust, machinery flooded by ruptured lines. Men who ducked for the blast find themselves looking up at daylight through a hole that did not exist a moment before. Photo interpreters later count cracks like lightning strikes. Engineers call it progressive collapse. Where bombs scatter force, Tiny Tim concentrates it where structure is weakest, converting the pen's own mass into a weapon against itself. One pass ship kill. How an escort went down. The same logic translates to ships. Escort destroyers and smaller escorts present less mass than a pen and more vulnerability in localized magazine and engineering spaces. A well-placed Tiny Tim could deliver a warhead to a critical compartment with terminal effect. Imagine the approach to a moored escort. The rocket aimed at the forward magazine combing or above the machinery spaces. Impact pierces hull plating. The delay fuse allows the warhead to penetrate bulkheads or deck, then detonates where confined. The explosion tears rivets, ruptures fuel lines, and destroys watertight integrity. A single well-placed blow can break the keel's continuity or send progressive flooding into adjacent holds. The ship lists, counter-flooding fails, pumps sputter and stop, and within minutes the hull meets the sea. Survivors describe the sensation as instant. One moment under weight of steel, the next rolling free and cold. On the attacking flight deck, the pilot sends the terse message: one hit, heavy damage. Probable sinking. Intelligence later confirms the slick and the absence of the escort on the morning record. Okinawa and the inland sea, where theory became reality at Okinawa. Tiny Tim cleared pillboxes and cratered revetments. It punched through hardened shore batteries that had blunted dive bombers and naval gunfire. In strikes on the inland sea and other harbors, the pattern repeated. One rocket, a structural failure, follow-on strikes exploiting the breach. Tight coordination between rocket delivery aircraft and follow-up bombers and fighter bombers multiplied the effect. The rocket opened the door. The next waves drove through it. Photographs taken from orbit and from carrier decks after attacks show roofs peeled back like lids, pens with exposed pen floors, and the dark rectangles of hulls now visible where concrete had previously obscured them. Intelligence summaries use the same understated phrasing. Enemy facility rendered inoperative. Repair time estimated months. The first combat uses of Tiny Tim did more than damage targets. They rewired the assumptions of harbor defense. Concrete was no longer an assured refuge. A single pass from above could convert shelter into trap. The psychological impact, crews surfacing to find daylight in what had been a bunker, spread faster than engineering assessments. Where once defenders felt safe behind meters of reinforced concrete, now every roof became a potential open wound. The moment fortresses became graves. Japanese reaction and the collapse of fixed defense. The morning after the first Tiny Tim strike, intelligence officers on the carriers argued quietly over coffee and film strips. Reconnaissance photos were looped. Analysts pointed to bolt lines and shear cracks. One image showed a pen roof split along a seam, concrete slabs leaning like broken teeth. Another showed the black rectangle of a submarine now visible where only a roof had been before. The language in the reports was clinical. Progressive collapse. Structural breach. But the human meaning behind those phrases was simple and raw. The defender's last sanctuary had been pierced in a single pass. Word reached Japanese command that something else, Something new had struck their ports. Telegraphs carried terse messages. Harbor pen breached. Cure, extensive damage. At Imperial Navy headquarters, engineers who had once boasted of meters of reinforced concrete now ran calculations for progressive collapse and shock transmission. Technical staffs pored over photographs, cross-section diagrams, and captured fragments to answer the same urgent question: how do you stop a one-shot structural incision? Field reports told a different story, closer to the human truth. Commanders at local ports described men who had slept under concrete ceilings and woken to rubble and sky. Submariners who had taken refuge inside pens reported oil slicks and diesel smell blasts that would follow hours later. Survivors spoke of compressed air systems ruptured by internal shock, pumps fouled with concrete dust, and power systems shattered by internal detonations. For many crews, the shelter became a trap, the route to the surface blocked, communications down, and escape routes clogged with falling slab and twisted steel. Reconnaissance and the silent proof photo reconnaissance became the arbiter. Pilots flew dawn missions over the struck harbors, capturing oblique and vertical images that would be studied by engineers on both sides. Analysts measured the length and width of roof failures, compared seam locations to building plans, and overlaid them with the rocket's nominal impact points. The pattern was unmistakable. Tiny Tim did not simply blow holes in concrete. It exploited structural continuity, the way slabs were tied to support columns, and how internal voids channeled blast into critical members. The rocket's penetration followed by internal. Detonation created stresses that led to cascading failures. Progressive. Collapse in plain language, Japanese. Post-strike assessments recorded each failure with a mixture of technical curiosity and alarm. They marked the usual countermeasures: deeper roofs, thicker rebar, added buttresses, but the diaries of naval architects read like a capitulation. One structural report bluntly observed, "Reinforcement by mass alone will not prevent internal detonation after penetration. Alternative approaches required." In other words, concrete could not be simply thickened forever. The method of attack had changed. Immediate tactical changes. The first operational response was practical and desperate. Harbor commanders issued orders at once: disperse ships where possible, deepen camouflage, cover pen roofs with earth mounds and timber, and create decoy structures to lure attacks. Where dispersal was impossible, the confined harbors of Cure or Sasebo, crews tried to increase standoff by adding earthen revetments and building sacrificial outer roofs. But these slow fixes could not be applied fleet-wide overnight. In forward units, small but telling changes appeared. Escort vessels were ordered to avoid mooring in exposed pens during daylight. They instead anchored in open water under smoke screens. Submarines were instructed to delay surfacing after air attacks until rescue or recovery teams verified rooftop integrity. Ports shortened the time ships spent in concentrated anchorages, moving them more often to reduce the risk of a single catastrophic hit. Yet each of these measures carried costs. Dispersal reduced logistical efficiency. Frequent movement increased fuel consumption and wear. Smoke screens hampered the defenders' own ability to spot submarines and incoming aircraft. The trade-offs were plain. Survival required sacrifice in readiness and local control. Doctrine rewritten. Under fire, perhaps the most striking change was conceptual. For years, Japanese defensive doctrine had been built on concentration. Concentrate your ships in the strongest shelter, conserve scarce resources in protected pens, centralize maintenance and fueling. Tiny Tim inverted that doctrine. The new rule became separation and concealment. Concrete accumulations that had been the essence of defense were now liabilities. Staff colleges and technical bureaus scrambled. Papers circulated under terse titles: countermeasures to deep penetration aerial rockets, reassessment of naval shelter construction. Engineers proposed layered approaches: outer sacrificial slabs, spaced internal bulkheads, compartmentation to prevent progressive collapse. Others suggested deception in the form of faux pens that might absorb a rocket's strike protectively. But all proposals suffered the same practical blind spot. They required time, steel, and labor the Third Reich could not spare in 1945. The psychological shock doctrinal and technical shifts mattered, but so did the psychological blow. Men who had believed concrete made them safe woke to a new paranoia. Ship captains refused to sleep below decks. Sailors clustered on open decks, shivering in the night air. Submarine skippers delayed surfacing for battery charge cycles, accepting battery limitation rather than risk concrete collapse. Words like collapse, breach, and progressive failure moved from engineering papers to boat deck conversations and cabins. Their very language changed to reflect a new existential threat. Shelter could be penetrated. Refuge could be converted into a tomb. Opportunity exploited. The Americans, for their part, learned to exploit the effect. Strike planners paired Tiny Tim deliveries with suppression of flak, P-47 or F-6F strafing runs to silence light batteries, then sent in rocket delivery aircraft at precisely calculated angles. Once a pen was opened, follow-on attack waves focused on ships made visible within the wrecked shell, or on repair facilities now vulnerable to incendiaries and bombs. One rocket's success could create a window of exploitation measured in minutes, not hours. Carrier commanders grew to value the rocket not only for its destructive power, but for its psychological utility. After-action intelligence briefs used the phrase door opening to describe Tiny Tim's role. It did not need to destroy every target. It only needed to create access. The subsequent waves finished the job. A final, bitter accounting. By late spring 1945, Japanese harbor defense looked less like engineering mastery and more like improvisation. The combination of tactical losses, material scarcity, and the terrifying vulnerability to single-shot penetrating projectiles convinced many senior officers that the old model of shelter and concentration was obsolete. The Navy shifted to token dispersal, occasional deception, and a grudging acceptance that many pens would remain liabilities rather than sanctuaries. The collapse of fixed defense confidence was a turning point. Tiny Tim had not merely damaged infrastructure, it had destroyed a belief system. The faith that concrete could make men immune to the sky. Where engineers and commanders once planned around permanence, they now planned for mobility and concealment. And in the rubble of those pens, in the slick of oil and the bent ribs of steel doors, lay the visible proof that a single unguided rocket, delivered in one pass by a brave pilot and a precise deck crew, could break more than concrete. It could break certainty itself. The short life and long shadow of the Tiny Tim. By summer 1945, the Tiny Tim had gone from prototype to combat-proven weapon in less than 9 months, a record even by wartime standards. It was the rare design that worked exactly as engineers promised and pilots demanded. But its triumph came late, in a war already tipping toward its end. Operational integration. After the Okinawa and Kure strikes, carrier air groups standardized their loadouts. Each squadron kept a handful of aircraft rigged for Tiny Tims, usually Corsairs or Avengers, the strongest airframes in the fleet. These were the door knockers, the first in every major strike. A single successful hit would expose targets for bombers and fighter bombers to follow. Reports from Task Force 58 summarized the new rhythm. Initial rocket penetration followed by secondary attack consistently effective. Target destruction often achieved within one sortie cycle. Tiny Tim quickly earned a reputation as the most reliable solution against hardened targets short of naval bombardment. Carrier commanders used it not only against pens and hangars, but also against bridges, submarine locks, and destroyers in repair slips. It became the missing link between bombs and guns. A naval shell fired from the air. Allied enthusiasm and rapid expansion production lines back home ramped up at a pace only late-war America could sustain. Douglas Aircraft, Caltech, and the Navy Bureau of Ordnance jointly supervised manufacturing. By July 1945, over 1,500 rockets had been completed and distributed to Pacific squadrons. Training films showed the launch procedure, ballistic curves, and damage footage, stark propaganda proof that no fortress is invincible. At the same time, the U.S. Army Air Forces saw the rocket's potential for tactical bombing. P-47N Thunderbolts began trials to adapt the rocket for airfield attacks in the Philippines. Army engineers even considered mounting them on B-25s and A-26s, though the war's rapid pace and the atomic shadow soon overtook those ambitions. The war ends. Before its peak, Tiny Tim's true campaign lasted scarcely 4 months. By August 1945, with Japan's surrender, its career ended as abruptly as it began. The final stockpiles sat crated on Pacific docks, some marked for Operation Downfall, the planned invasion of Kyushu. Had that invasion occurred, entire squadrons of Marine corsairs were slated to employ Tiny Tims against coastal batteries and hardened bunkers ahead of the landing forces. Estimates predicted penetration depths up to 3 meters of reinforced concrete, enough to neutralize the gun positions guarding the invasion beaches. Instead, the weapon's ultimate test never came. Hiroshima and Nagasaki changed the war overnight. The rocket that had made concrete obsolete was itself rendered obsolete by a flash of nuclear light. Post-strike analysis, in the quiet months after victory, the Navy compiled exhaustive reports. Engineers revisited strike footage, measured crater radii, and compared pre- and post-attack reconnaissance. The conclusions were unambiguous. Penetration, 18 to 24 inches of reinforced concrete, full breach at impact angles under 20 degrees. Warhead efficiency, 90% of explosive energy transmitted inside target structure. Reliability, over 80% functioning rate, astonishing for a weapon rushed from concept to combat. A report from Commander, Naval Air Forces Pacific, summed up what many already knew. Tiny Tim rendered fixed naval defenses untenable. No further reliance should be placed on static protection against aerial penetration weapons. Those words would echo into the next generation of armament. Design, the birth of the rocket doctrine. Tiny Tim proved a principle that mass-accelerated penetration was more decisive than size or altitude. It bridged the conceptual gap between unguided weapons and the coming missile era. Designers at China Lake and White Sands immediately began adapting its lessons. Improve propellants, add guidance, reduce drag. Within 5 years, that lineage produced the Bat glide bomb, the Tiny Boy experimental missile, and eventually the Bullpup, the first truly guided air-to-surface rocket. Naval architects, too, adjusted. Post-war shipyards abandoned monolithic concrete pens in favor of dispersed shelters and camouflage. The hardened pen, once the symbol of industrial invulnerability, was quietly retired from new designs. Japanese reflections in post-war technical exchanges. Japanese naval engineers studied the fragments left behind. Their reports were precise and melancholy. No reinforcement by concrete mass can prevent internal detonation of rocket-type weapons. Defense must depend upon concealment, dispersal, and deception. The sentence was a death notice for fortress doctrine. Every future Navy would read it. From an unguided lance to the age of standoff firepower. Tiny Tim's combat career was brief. Its legacy was not measured in years, but in ideas. In the way a single new weapon rearranged priorities in ordnance, shipbuilding, and the calculus of coastal defense. What the rocket demonstrated in months, engineers and strategists digested for decades. The immediate operational lesson was simple and brutal. If an aircraft could deliver kinetic energy with the precision of a naval gun, then air power could substitute for, or at least dramatically extend, the reach of surface fire. Carrier strike doctrine evolved accordingly. Strike packages began to include a door opener element. Aircraft tasked specifically to deliver a Tiny Tim on a critical seam or structure, followed within minutes by conventional dive bombers, rockets, or strafing fighters to exploit the breach. Commanders learned to choreograph strikes like a siege engineer sequencing sappers, not mere bombers dumping explosives. That lesson migrated quickly into planning for large amphibious operations. Planners for the canceled Operation Downfall envisaged Tiny Tims softening beach defenses and penetrating gun revetments that naval gunfire might not neutralize quickly. The weapon's ability to turn a hardened, immobile target into a temporary aperture for follow-on effects reshaped assault thinking. Air power would not only suppress but physically create pathways for invasion forces. Technology and the road to guidance. Technically, Tiny Tim proved an important thesis. Mass and velocity, when combined with an appropriate fuse and hardened nose, could reliably defeat armor and concrete. That notion, concentrate kinetic energy into a focused, penetrating impact, became a cornerstone of post-war munitions research. At China Lake, Dahlgren, and White Sands, engineers who had worked on the rocket began projects aimed at increasing accuracy, reducing weight, and testing alternative propellants. The next logical step was guidance. If a rocket could be made to fly straight enough and be small enough, adding control surfaces and an explorer's mind could transform one-shot effects into standoff precision. Within a decade, the ideas matured into early guided air-to-ground weapons, glide bombs, television and radar guidance experiments, and the first generation of seeker-equipped missiles. Systems like the Bat and later guided rockets and missiles inherited Tiny Tim's conceptual DNA, hit the hard point, not the general area. Tiny Tim therefore sits in the lineage between unguided ordnance and the precision munitions that defined Cold War strike capabilities. Shipyards, pens, and the new geography of defense naval architecture and harbor design changed in response. The era of single large pens and centralized repair basins gave way to dispersal, concealment, and smoke screening as the principal means of survival. Where once concrete and mass were the primary counter, planners favored redundancy, multiple smaller slips, camouflaged revetments, and the capacity to move vessels rapidly. Shore infrastructure designs incorporated sacrificial elements and modular repair, acknowledging that some damage could not be prevented but might be contained. Japan's post-war technical reflections were blunt. Continued reliance on monolithic shelters was a vulnerability. Their engineers recommended dispersal, deception, and mobility, a doctrinal pivot embraced by navies worldwide in the following decades. Psychological and strategic ripples. Psychologically, Tiny Tim punctured the complacency defenders felt behind concrete. The shock of waking under the sky was not merely structural damage, it was a crisis of faith in protection. That loss of faith imposes operational costs greater than a single destroyed pen, altered anchorage patterns, shorter in-port times, and a constant need to rehearse contingency movement. All of these strain logistics and tempo, the invisible taxes of modern warfare. Strategically, Tiny Tim accelerated the shift toward standoff engagement, the idea that you should be able to disable critical nodes, bridges, locks, pens, ammunition dumps, from a distance with precision rather than exhaustively pound them with mass. That shift played out through the Cold War as missiles, precision bombs, and guided munitions matured. Tiny Tim did not invent precision, but it proved that where precision matters, a single accurate hit can be decisive. There's a peculiar humility in watching a fortress fall to a single, unguided streak of metal. The image is almost biblical. Centuries of labor, concrete, rebar, the sweat of builders, undermined in a breath. Tiny Tim did what vast fleets and countless bombs had not. It concentrated force into a small geometry and let physics finish the argument. That is a moral as well as technical observation. Humans will always build protections, but innovation often asks a single, quiet question of those protections. What happens if we change the shape of the hammer? The men who made Tiny Tim were ordinary in their craft and extraordinary in their persistence. Laboratory failures and brutal field tests taught them as much as any doctrine, and pilots who trusted their aircraft to carry and launch the giant rockets accepted a personal wager between courage and invention. On the other side stood crews who had once slept under sealed concrete, who had thought themselves beyond the immediate reach of the sky. When the roof peeled open and daylight fell where there had been none, their world shifted. The loss was measured in ships and pens, but the deeper tally was trust in permanence. Technically, Tiny Tim is a footnote in the history of weapons, an unguided rocket among many. Strategically, it is a hinge. It signaled the end of an era in which sheer mass of shelter and ordnance decided outcomes, and opened the era in which velocity, precision, and timing became decisive. The principles it embodied: penetration, delay fusing, concentrated kinetic energy, returned in later generations of missiles and munitions, refined by guidance and electronics into tools that can reach farther and strike truer. And there is a human lesson here. Every defense invites a counter. Every wall that looks permanent will be tested by imagination. The builders of the pens and the engineers of the rockets were each pursuing preservation in their own terms, one through mass, the other through motion. In the balance between permanence and change, history has a habit of siding with the latter. In the quiet that follows the blast, the smoke thinning above a breached roof, what remains is not merely rubble, but a question for those who rebuild: how will you protect what you value? Knowing that tomorrow someone will try to break it with an idea,